Okay, resuming where we were. Now, I mentioned last time that I thought possibly something may have been missing for problem 5. And I thought that what was the part that was missing was a method for constructing an isosceles triangle. However, I try as I may, I couldn't come up with one. I thought, and again, this goes back to making assumptions where you're not allowed to make assumptions. I thought that there was nothing to it. You want to make an isosceles triangle, all you do is make equilateral, right? And then take these points here and extend the line, right? Since this is clearly a bisector, and then these lengths would be equal, and then you would have an isosceles of any base you want and any height. Forgetting, of course, that I have not yet proved that this is a bisector of this line, and in order to do that, I would need to be able to provide evidence that either that these are right angles, I don't know how to show, or that these lengths are equal, don't know. You might say, well, that's completely symmetric. That's true. And that would be a valid argument if we had anything in our axioms to do with symmetry, and we don't. Symmetry is not given in the axioms. There's nothing that I can see that allows us to make a deduction based on symmetry. It equals added to equals, whole is greater than part. There's nothing here. We got this. It's the only mention of right angles. Magnitudes that coincide are equal and fill the same space are equal. Now that maybe might do it, except that this here is a mirror image of this, so you can't really place this triangle on top of this triangle because it's a mirror image. There's no way to rotate it or anything. All I know is that they share these two sides in common. I don't know if this angle is equal to this angle. Right? It's not a given. If you think that that's a given, then you're making an assumption, right? There's nothing in the axioms that says that, right? Try to find something in here that tells you that those are equal, and then you can say it. But there's nothing. There is nothing. This construction of this triangle, I can say is equal to this triangle because I know these lengths exactly. I know this is one radius distance, the same as in this triangle, and I know these distances are the same as these distances. So I can draw an equivalence between these two, but again, these are mirror images, so there's not much I can do with them. Until we can show that an argument by symmetry is valid, not shown, then we don't know that this is a perpendicular bisector, and we can't say anything. But there are examples that one could come up with where you can draw this figure and this is not a perpendicular bisector. Believe me, it can be done. Because what you're viewing here, right, is how can I say? Imagine your view of the world is such that you live in a two-dimensional surface, but that two-dimensional surface is all bent and twisted, right? And you draw what you think looks like a perfectly even circle, right? But in reality, it's not. Like the distances are might get all warped out if you extend too far or something like that. In a strange, if the geometry of the world that you're living in has unseen curvature or something like that to it, then things that look flat to you might not be flat at all, and so sorts of comparisons wouldn't be valid. Like if you think of that picture that people always show. Say this as 10. A good way to generate it maybe with a log function. Not that one. Whoops. Get rid of that dumb message. Go away. Not rotated. But I meant more, less, and means inclination intersect with increase inclination. Oh, I can decrease this to little. Inclination at y equals 0. Oh no, it has got to be bigger. The other way around. Inclination meaning slope. That's not too bad. Now what I want to do is rotate this in this direction. How would I do that? And change the offset. Oh, I know. Well, let me think now. Put the axes here for a minute. If I want it to be like a Z, have a Z, I'm trying to draw a funnel, okay? I'm going to make an ellipse to use as a guide. X 150. Y, want it quite skewed, centered. Oh, no. 150, that's a double. I made it a little bit more skewed. Now, all I want to do is rotate this and be able to be looking at it from a different angle. Let me do that. Rotating this way is no good, and that way is no good. But if we start out with a big angle, it's not you, the log function. And rotate this way. Or give it less and less rotation. I'm just curious. When I reduce this, what do I get? It's going that way. If I'm increasing it, doesn't matter. I can try and draw my own picture. Use the handwriting. Whoops, it's not very good either. So, if you're living on one of these weirdo surfaces, which are impossible to draw, I don't know. And in the background goes like that, and imagine that there's a, some kind of curvature, and this curvature gets smaller and smaller as you go down. Well, then, although you may not, you viewing your universe in in the comfort of your home, may not know it. Your world is curved. And so if you draw a circle here, it might appear to you like a circle, but your universe is lopsided. You know what I mean? Come on, this thing won't give me anything unless I have enough points. There we go. Right? And so drawing a line here and a line here and saying that by symmetry this side equals this side might not be true in reality if you lived on this weirdo surface, right? Well, that's the case with this diagram. It might appear as though you can say, oh yeah, well, by symmetry these are going to be the same, but there's nothing in the axioms that says that. We have to prove it. It might be that it follows, given the axioms, that the axioms amount to saying that we're not living on a weirdo bent curve volume or surface, and then it's fine, but we haven't gotten to that point. However, the problem doesn't really require us to construct one, I don't think, or the theorem rather. All we need to do is follow the axioms and see if we can produce the result. The result is to show that these two angles, the blue ones, are equal. So in an isosceles triangle, if now the equal sides are given because it's an isosceles. If they be produced, that is extended, the external angles, external means this part, not internal, external. So along the production of this line, or along its product, from the baseline to the product line, and the internal angles of the base are also equal. So that's what we have to prove. Now the fact that we have to prove that emphasizes my point. This would be, if you took the naive approach that, well, it's symmetric, so they must be the same, right? Then you're making an assumption that isn't granted by the axiom. The axioms don't say that. There's nothing in the axioms that says that symmetry is a valid argument. It may just be that symmetry is valid, but we have to prove it. And this is one of the things that will help establish that, in fact. And we will be able to show that thing is a perpendicular bisector. But we need this first. So in order to do that, we do what we can. We're allowed to produce to any amount we like a given line by a given amount, right? That much we're allowed to do. It says postulate 2. Postulate 2. We now have the mark, easier to find. Okay, we can produce a finite straight line to any length in a straight line. So that means the yellow part is arbitrary. Okay, the red's given, but also arbitrary and unknown, and we can extend that arbitrarily further. And that's the yellow bit. Now, take yellow equals yellow. This says problem 3, which would be this one, which says something about being able to cut something off. Yes, I suppose so. Would that be required? You see, in order to reproduce this yellow extension over here, it's simply a matter of drawing a circle with this as the center, and this is the radius, right? Then this would also be a radial line, provided this length is equal to this length, because that's the definition we have for a circle. So I don't know how problem 3 helps. That says that we can cut something off. I see. So we take whatever the produced part is. Problem 3 allows us to cut it off and isolate it, and use it to extend, to extend this line by the same amount, but I don't really see why it would be needed. In fact, it's more like using this one, proposition 2, which allows us to take a, well, no, that one won't give, that proposition 2 allows us to draw this bit at this point, but we still have to be able to, measure this bit off, and problem 3 allows us gives us a means for doing that. Right? We have a line. We extend it. That gives us two lines, really. We have the red line and the produced line, one longer than the other. And this thing here says to cut off a part equal to the lesser of the two, which also means to cut off a part equal to the greater of the two, right? We could do that too. By cutting this part off, we get two pieces, one lesser and one greater. So basically, this is a procedure for cutting a line into two bits, one bit equal to some part that is given, in this case arbitrarily, but in our case the one we added ourselves, so it's not totally arbitrary. So I would say that it appears to me as though problem 3 is not really required. All one would do is you take out your compass, let's say like that, and you go like this, right? And then you go here, and this line is already given, and so we would extend this length to E, and therefore, by definition, these two lines are the same, it's equal length. Okay. All right. Given that we can do that, and also we are part of the procedure here is to draw these two lines. I've already done that. Okay, and I've also indicated what we're trying to prove. This should be blue. Blue because I drew the angle blue. Okay, so the theorem states we want to show these are equal and these, what they call the exterior angle, these two are equal. Keep in mind as well that we do not yet have anything that tells us that the sum total of angles along a straight line that is cut by another line adds up to two right angles. We don't have that in the axiom. All we have is that if it's equal, it's two right angles, but not anything else. By the way, this parallel postulate, I said last time that it became an axiom, but that's not true. This parallel thing was demoted from axiom to postulate. Well, I don't know if that's demoted, but it is a thing that is that doesn't take the form of an axiom, but takes the form of a procedure or an ability or a device that we're allowed to use. Okay? Now, it may follow that because of the way this is worded, it says that if two lines, of course it's two lines, not one line, fall on a straight line and the sum of the interior angles is less than two right angles that they meet on the side where it's less, it may follow from that the sum of the interior angles on the other side of the straight line must be greater than two right angles. Otherwise, we would have a situation where the lines meet on both sides. But I don't know. It doesn't say that. And there are, in spherical geometry, they do meet on both sides, turns out. And the angles are right angles. We take a sphere, let me go back to my phase. Take a sphere It's a little bit difficult, but I don't know, a bit bigger than that. Range, full circle. Bigger. Too big. Whoops. Alright, ellipse. Just trying to draw the earth quickly. What did I say that was? 230. Just want to try and make it look as three-dimensional as possible. There. Okay. Here's the equator. Now the lines of longitude, I guess they call it, could be given by ellipses. That would be 101, something like that, right? Like this. Here's a line of longitude. I'll try and make another one. Something like that, right? Alright. That means this has got to go here, sort of. Oh, no, that's not right. They don't bunch together. They bunch together up here and flatten out near the equator, so this is not the right picture. But anyway, I'll try the handwriting. I'm no good at it. Something like this. And eventually it's a straight one. And then on the other side it's like this. And then getting more and more bent, right? These are right angles here. And these geodesics that go right around the Earth, let's say, are the equivalent of straight lines. And they all meet on this side, and they all meet on the other side. And they all make right angles on both sides of the at the equator of a perpendicular line, straight line. Also a geodesic line. So here we have perpendicular, 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 and they meet on this side and they meet on this side. So you can't take that for granted either. This here doesn't tell you that just because one side might have things adding up to less than 2 right angles, that the other side must add up to greater than 2 right angles. You gotta be careful. It does turn out to be the case in Euclid's land, but it hasn't been proven. All right. Now in the figure, we have these things, and we're trying to prove that these angles and these angles are the same on both sides. Symmetry is not a valid argument. And we also draw these blue ones. Okay, the blue ones are drawn so that we can identify these little angles for these triangles here that have a blue base. And what we do now is we separate out just for no reason whatsoever. What we're going to do is take A, C, D, B, if you like, this great big one, and this one, and pull them apart to make 2 new triangles. I might as well use the other thing that I ruined. And those look like this. So we have a red line, and that's extended by a yellow line, some amount. Let's draw a rough diagram. Another red line by hypothesis equal in length to the first red line. Okay, and the blue line, which corresponds. These ones correspond to the ones that were filled in the bottom. I can make a small version of that thing. For reference. Just so you can keep track of what's going on. But that's the shape in the other diagram. So now this part is pulled out from this side, and the other part sort of this in reverse. Whoops. Okay. All right. Now, by hypothesis, the reds this red is equal to this red, and these two are also equal. But in particular, the yellow was constructed to be the same length on both sides. So this length and this length are the same. Okay, and so that's by construction. And the black angle, which I'll have to indicate as white, are common to both of these triangles. That's this angle here. Let me just start, I think we can just do it. Okay, that's this angle. Alright, so now we have two sides the same and a common angle, which tells us that the base is the same. By the previous problem. Previous problem told us that two sides the same and an angle in common means the triangles are equal in every possible respect. Okay? So in particular, what does that tell us? It tells us the blues are the same. It tells us this angle and this angle are the same. Now, this angle, these ones are the reds. And they're the same. Everything is the same on these two by the previous theorem. And similarly these, which have been indicated as a as a sum, this blue angle, right, plus this yellow angle are presumed to be this angle. By the way we constructed this thing, this is now being asserted as a consequence, because these are the same. Whatever color this is, it isn't given a color. Black? No. This here angle is this angle. See? And we know the same by the previous theorem. So this angle here, which we're writing as the sum of the interior angle of the isosceles plus the extra bit included for this triangle, is the same on both sides. Okay, so if I draw a white line indicating the original white line, and a blue thing here, and then whoops, and then a yellow thing here, okay, then similarly on this side they add up to the same thing. That was proved in the last theorem, as I mentioned about 12 times. Yellow. Okay, so these are the same. I don't know. Grab that. Yeah, look the same, but you get the idea. Equals. All right. Okay. Now that's something that we couldn't have said before having proven a previous theorem. Blue equals blue and red equals red. I already mentioned blue here, not meaning the angle blue, but the blue line. These lines are the same. Now, in this triangle, taking a different chunk of the construction, this here is another triangle that was formed from these blue lines. So the yellow, the black or white for me, yellow, white, blue. Yellow, yellow, white, well, we'll do it on both sides. White, here, blue. So these triangles, right, are taken from here and here, have yellow in common, right? And the red equals red. Red is these angles, which won't copy well from there. Let's make it a triangle. Okay, those are common. So we got a common. We got these equal, another common angle, actually, and the yellow is equal. These are completely equal in every respect. Right? We know that the yellow angle, which is the one in the corner, this one, that those angles are equal. And the reason we know that is because this is the same as this is the same as this, and these two sides are the same. And in fact, this one could be turned upside down and put flush against this one. So by the same reasoning from the previous problem, in fact, they say by problem 4, the yellow angles are equal. However, using the axioms, it turns out that we've already established that yellow plus blue is equal to yellow plus blue. And we have yellows equals. If equals are taken away from equals, then the result is equal. Right? That's axiom tells you. Axiom 3. Not appealing to any thinking. You're not allowed. Three. No, that's the definition. Axioms. Equals taken away from equals, remainders equal. So we have these are equal, and we have yellows equal by theorem 1. And so therefore, the blues are equal. Well, that was one of the things we were aiming to prove. right? That ABC is ACB. So we've done this. I thought I changed this to blue. I did, but I didn't save it. So done with this part. Next, we just need to show that these angles are the same. Going back to our scratch board, and here, this follows right away. No, okay. Well, we did that part. Oh, I see. Part of it. No, I'm missing a step here. Not there. Okay, well, oh, here it is, here, I see. Again, from problem 4, that exterior angle is this plus this remaining bit which they've drawn as a hollow polygon. Like that. Alright. Now, it says from the last theorem that we should be able to establish that these empty ones plus the yellow are equal. Okay, let's see how that works. This is equal to that. Now, why is that? Problem 4. Well, everything about the triangles is the same. Now, wait a minute. The little triangle is this one. This is the big one. Well, this figure is an exact copy of this figure. So it's certainly true, right, that since this is the same, right, on both sides, and this empty part is constructed using this line and this line and taking the angle of inclination between these two. Well, that angle of inclination has to be identical on both sides because the figures are identical, right? So therefore, this sum and this sum, I guess, must be equal. Is there another way to make it even clearer? We could extend this side. We could, if we wanted to, extend this side by an amount yellow, right? If we wanted to. And that would make these two sides the same and this an equilateral triangle. And we could do the same here. And then we could close this off, let's say, with another line, a white, almost white line. Let's see if that does it. Well, in this case, these are identical equilateral triangles. And this triangle are identical, so they coincide. This length is the same as this length in this one, and blue the same, and white the same. In fact, all sides the same, so therefore all angles in this triangle must be the same as in this triangle, and so therefore this empty part is the same for both of these triangles. And so that means that for the left one and the right one, the sum of these two, which is called the exterior angle, is the same. So we've now established the last bit, and I'll save this. The last bit of the theorem, that these angles are the same. These are the same, and these are the same. Okay? And we still don't know, unfortunately, whether or not these add up to two right angles. Now, is it possible to show it? I don't know. I'll have to think about that, because I'd really like to be able to say that that's true. Because once we've got that bit, then we can get to the bit about the sum of all angles of a triangle adding up to 180. We don't have that yet, by the way. At this point, even though we know the Egyptians are jumping up and down, stressing and calling us a bunch of idiots for not seeing it, we do not have evidence, proof, that the sum of angles in a triangle is 180 degrees. But we'll get there. See ya!